Okay, next slide. Thanks everybody for joining. Sorry for that little delay. For anybody, any newcomers not aware, just by way of introduction, OpenEXR is the reference implementation of the high dynamic range image storage format for the motion picture industry. Originally developed at ILM in the late 90s, open sourced in 2003, practically legal drinking age now. Contributors from ILM, Weta, DreamWorks, and a whole lot of others over the years. Charter member of the Academy Software Foundation 2019. We have 3 GitHub repos that we maintain. The main OpenEXR repo that project that implements the file format. iMath is a lightweight implementation of vectors and matrices, and we have a gallery of images as well. Next slide. Steering committee, I'm Cary Phillips, Industrial Light and Magic. Christina Templar-Leitz is here from ILM as well. Joseph Goldstone from ARI. Kimball from Weta FX. Larry Gritz from Sony. Nick Percino, Pixar. Peter Hillman at Weta, and Rod Bogart at Epic. I think we're all here today. Next slide. So we're going to go over just a quick recap of the current 3.1 release, talk about what's going to go into the 3.2 release that should come out mid-August, and then the bulk of the time will hopefully be spent talking about some experiments in GPU decompression and real-time streaming. Next slide. So 3.1 came out about a year ago or so, and the major feature was Kimball's new implementation of the library OpenEXR core, a ground-up rewrite in C that's much more thread-friendly and performant. It's been nearing completion over the last year. The most recent addition was support for the DreamWorks compression formats. Lots of other tweaks along the way to make sure we're optimizing performance, mostly in the form of making sure that we're using all of the available intrinsics properly. Lots of build and bug fixes, and we finally got around to modernizing the website and a gallery of test images to go with it. Next slide. A few other developments. One encouraging thing that happened recently was MacPorts finally got around to modernizing their port, so you can install OpenEXR on a Mac now and get the most recent version, which is was really nice. Another thing that we had just recently, the developers behind the Python bindings for OpenEXR, what you get when you do pip install OpenEXR, reached out to us. They have had nothing to do with the project officially until recently, but they're interested in turning it over to us. This has been kind of a thing on our back burner to try reining this in, because it's not something that we've typically been responsible for, but we will be going forward. Nick, you want to say a few words about USDZ and OpenEXR?
Yep. So OpenUSD 23.11 arriving late this year will have core OpenEXR support. So that means that if you're using USD imaging and Hydra and things like that, it'll allow us to understand what to do with OpenEXR files, regardless of which plugins have been compiled and which libraries you're linking with. USDZ is our zip packaged USD archive and distribution format, and it also gains formal OpenEXR support. So this opens the door to consistent handling of HDR imagery in platforms and applications that rely on USDZ. Coming shortly, we'll be publishing over at AOUSD the specific features of OpenEXR that are supported out of the box, how layer support works, and so on. Some advanced features aren't initially supported, particularly deep pixels and cube maps. Overall, we're pleased to take this step forward, making OpenEXR technology always available in USD, and would also like to thank all our partners who helped make this possible.
Another thing, kind of out of the blue, somebody from the Coalition for Content Provenance and Authenticity reached out to us recently with a question about storing binary blobs in EXR headers. And Larry, you want to say a few words about what that was?
Sure. Yeah, with the caveat that I'm enthusiastic about this project, but am not an expert. So apologies to the actual experts if I mangle part of this. But the basic idea here is, I think we're all, kind of watching the news and the world carefully about how some of the new machine learning based imaging technology, among other things, can make it very tricky to tell what images have been manipulated or not. So this is an initiative that's driven by Adobe and several other companies for essentially a metadata standard to be able to attach to images that sort of document the original provenance and successive changes that have been made to an image. And the sort of big vision is eventually, you're on the internet, you see an image in the browser, and there'll be a little thing on the corner that says like, yes, this is a, certified image or whatever. And you poke on it and it can give you the list of like, where did it come from and what changes have been made. And, I think in their vision, images that don't have these, this metadata, maybe you think, maybe I shouldn't trust this. I think it's a really interesting initiative, and I'd like our projects to support that in the ways that they can. Some of the Adobe products and others are already starting to put facilities in so that as they write media, this metadata can get attached optionally. And so we don't want to just drop that on the floor when it comes to our software. So anyway, this is just kind of the beginning of our collaboration with them. But I'm very intrigued to see where it goes. I think it's a worthy effort out there in the world.
The guy who reached out is planning to come to our next steering committee meeting to kick off the discussion, explain more about it. So that's feel free to join. Let's see, next slide. So we're on the cusp of releasing OpenEXR 3.2, which will go into the VFX reference platform for next year. Next, we'll talk about some of the components of that. In fact, Kimball, you want to take over and talk about libdeflate?
Sure. Yeah, so one of the things that we've done in 3.2 is actually switch from using zlib to using libdeflate. And so I did want to point out that this does change a new dependency in that the main OpenEXR library now depends on the core, and so is starting to switch. And actually, the implementation of the deflate library and all that sort of stuff is only in the core. The other thing is that libdeflate can easily be vendored into the EXR libraries. There isn't actually an external dependency on that, which helps for cross-platform support fairly radically. But yeah, so that's sort of the big change there. We've actually pushed one change up to libdeflate library itself to that'll be in. I've forgotten the version it'll be in, but that makes it even more sort of thread safe if you are doing your own custom allocators within OpenEXR. So if you're overriding what malloc and free are, this will be more thread safe. The other thing in 3.2 that we're switching to, and I don't know that will be. I think there will be another ABI switch after 3.2, but one of the things that we're doing with this is trying to get to a mode where when we release a new version of OpenEXR, we don't necessarily have to have everybody recompile everything all the time. Obviously, not for patch releases, you don't, but for if we add a new feature in 3.3 or 4.0 or something like that, you don't necessarily have to recompile. And so maybe this isn't so much ABI compatibility, but we are taking a strong look at that basically and trying to be more backwards compatible going forward, such that and this is primarily driven around how much OpenEXR is deployed into operating systems. And I think the long-term goal for that is to get one of those little up and down arrows on the VFX reference platform page that allows you to use a newer version in your facility or whatever. So that's something that we're starting with 3.2, and there'll probably be some refinements as we go forward. And then the optional camera metadata, Cary, do you want to, or Joseph, do you want to, are you talking about that?
Yes, I would be.
Yeah. Is there another slide that I need to go to?
There are 4 additional slides. So go to the first one first.
Yeah.
Okay, so lots of stuff here. It is almost all in support of better compatibility with, or better emulation of physical cameras. So automated editorial workflow, there's some new attributes there. Forensics, if you find out that there was an issue with a particular camera firmware, for example, you want something that can help you isolate which other shots might have had that issue. If you have to do a pickup shot, we can record some of the key camera settings. And if you are doing metadata-driven match move, which the Foundry has done some amazing demos of, we are providing a host of attributes there. Next slide, please. So we're not making these up out of thin air. There's actually quite a bit of work right now on much of this metadata coming out of a Society for Motion Picture and Television Engineers, SMPTE, an effort they are making to promote interoperability in virtual production. So one of the key things there is getting to where when 2 different vendors of some product say, we give you metadata for X, that 1, it means the same thing, 2, it's named the same thing, 3, the units are the same, and 4, the data representation is the same. So we've been working on that, and I'm a part of that group. I'm a steering committee member, so we've reflected a lot of that work back in here. Next slide, please. The first thing here just recaps what I just said. Cary, you assured me that that all of these slides would be almost instantly available, right?
This afternoon.
Okay.
Not instantly, but the next best thing.
So where could people go to get, how would people find those so that they're not spending their time right now writing down these URLs? Because that's what I don't want.
I'll make a post in the news section on the website.
Perfect. So thank you. SMPTE maintains 2 GitHub repos, which is very daring for them. They've normally been a much more closed organization when it comes to coming up with stuff like this, but anyone who has a GitHub account can file an issue or submit a PR. One of them is on essentially what the definitions are, and then the other is contributions by various camera vendors to show how their particular camera output would map to these normalized definitions. And then those normalized definitions are the ones that we just added to OpenEXR. Next slide, please. I wanted to just put in a plug here for a paper that just released yesterday. much of the work that we did on the trickiest definitions comes from this paper from Cook Optics. And it's really a tour de force for people who have always wondered, how does the world of optics and the thick lens model match up with CGI and a pinhole camera model? So that's what this will tell you. And please check it out. And that concludes my section. Thank you. Oh, oops. Well, not quite. A couple more things that we will have coming. We'll keep tracking the SMPTE thing. There'll likely be some additional metadata for supporting various lens distortion models. We'll consider adding that. Provide an example of how to take a real-world camera and match the model to a CG camera and the traditional RenderMan-inspired attributes here. I think it's finally time to kill off 2 attributes in the existing implementation that, as far as we know, have never been used. The rendering transform and the look mod transform, which were intended to carry or point to CTL, the color transform language. And nowadays, the up and coming way of specifying what those transforms are is the ASIS metadata file. And so we are planning on retiring these in favor of that. And next slide. Yeah, I really am done. Cool. Letting go.
So Kimball's new core library, I know, one of the main design features behind it was to put in place a more modern and accessible IO pipeline, sort of working towards being able to do decompression on the GPU, kind of independent of that. Rod and some other folks at Weta, at Epic, sorry, have been experimenting with just that. So they're going to tell us about what they've done. Rod and Russ, you want to take it away?
Yeah, I'm going to hand it straight to Russ. Russ has been doing some work here with trying to do GPU decompression, and we've done a little bit of that at Epic anyway. And so none of this is within the Unreal Engine. All that you're going to see here are examples of test programs that we've done outside the engine. So this is not to say that it's necessarily part of anything that we're doing in the future in Unreal, but it is promising for the future of what EXR can be. So I'm going to let Russ go ahead and present the rest of this.
Thank you, Rod. Could we go to the next slide? So I'm just going to blast through the motivation for this experimentation. At Epic in Unreal Engine, we utilize EXR to play high quality HDR sequences. 1 frame for 8K, which is 8192 by 4096 RGB, 16-bit per channel, takes about 192 megabytes, roughly 200 megabyte per frame, which means that to play a 30 seconds of uncompressed 8K EXR, we need 140 gigabytes of disk space, and that's just 30 seconds. On top of that, it has a very high bandwidth requirements for PCIe because you need to transfer 200 megabytes from your hard drive to the GPU, and you do it through the system memory. So you need to read into system memory, then decode the EXR data, and then copy to GPU. So each one of these processes takes quite a bit of time. So 200 megabytes on PCIe 4 or NVIDIA GPU, NVIDIA Quadro A6000 GPU, it takes about 45 milliseconds to copy. And that stacks with the requirements for Unreal Engine itself, such as meshes and particles to be rendered. On top of that, we have a hard drive disk. Well, I mentioned the disk space, but also the disk read speed. So to play at 24 frames per second to 100 megabytes per frame, you need roughly 4.8 gigabytes per second disk speed, and an average disk is about what the NVMe M2 hard drive is about 3 gigabyte per second rated. Next slide. So our current best implementation, which is what you see on the right here, it's spread across 2 frames. At the beginning of the frame 0, we read data into structured buffer, which is accessible to both CPU and GPU. It takes 50 milliseconds to read from NVMe into structured buffer, and then a synchronous copy over 2 frames. So by the frame 1, over 1 frame, by the frame 1, we get data in a structured buffer, we decode it, and we produce a texture. So the asynchronous copy is somewhat negligible, but if we stack the 2 together, you get 70 milliseconds, at least 70 milliseconds of frame time. So with this approach, we are able to play 15 frames per second, 8K 16-bit EXR. We improve that frame rate by utilizing tiles, and we get 24 frames per second, depending on the screen space of the EXR. But we still have the 2 biggest remaining problems. One is the hard drive speed and space. So as I said, 30 seconds of 8K XR take about 140 gigabyte of hard drive space, and the slow throughput. So there are high hopes for PCIe 5 and 6. What you see here on the left is a screenshot from Unreal Insights, which is our benchmarking tool. It shows that it takes to copy EXR data to 100 megabytes on PCIe 3 in this case, 50 milliseconds, which is a substantial amount of time. It's slightly faster on PCIe 4. Next slide, please. So this is how it looks in the prototype. This prototype implements the reading system exactly how it is in Unreal, almost exactly how it is in Unreal, without the synchronous copy. So what you see here, it takes roughly 13 frames per second, which is a terrible frame rate, but it's 35 to 50 milliseconds to read into shared memory, which is again a system memory, 40 milliseconds to copy from system memory to VRAM, and 0.4 milliseconds to decode EXR into actual texture. That equates to roughly 75, 80 milliseconds or 13 frames per second. So it is improved further in Unreal Engine by copying asynchronously and displaying the results the next frame. Next slide, please. And this is a snapshot of this prototype that shows the spread of the GPU during that frame. You can see up the top in green, it says that frame time is 73.5 milliseconds. And you can see that the first half of the frame on the GPU is empty. This is where we read on the CPU into system memory. And then the second part of the frame in green at the actions row, you'll see that there is a copy buffer region. And that is when we copy from system memory or shared memory into GPU, which is again a substantial amount of time. And total time is 73.5 milliseconds. Next frame, please. So this is a short summary of the reasons why we looked into this, and now the solution. So the first part is NVIDIA's GDFlate. GDFlate is NVIDIA compression decompression algorithm that is GPU friendly. It can be done on GPU, but also has CPU fallback. And it's based on Deflate, which is used in zip and PNGs and in many other places, with a compression ratio of 1:2, which is achievable. You essentially improve the PCIe bandwidth cost from 200 megabytes per frame to 100 megabyte per frame. And of course, it reduces the disk speed requirements as well as the disk space requirements by 2 as well. So this is the main advantages of this. In the little diagram below, you can see the very high level workflow. So you read compressed into shared memory, so system memory is still utilized, and then you copy the system memory into I'm not sure what's happening, into
I don't know what happened.
No worries.
The computer just decided to switch screens.
Into temporary buffers on the GPU side, and then it decompresses it and produces a texture. So next slide, please. This is the second part, which is direct storage. It can, I'm comparing direct storage to GPU Direct, which is NVIDIA's framework that allows to read directly from NVMe hard drives into GPU, skipping the system memory, meaning that you do not need to allocate system memory, you do not need to do buffer juggling, and you just reads directly into GPU. So Microsoft's direct storage API implements both. It allows you to read directly into GPU and decompress at the same time. So it implements GDFlate. For that reason, we chose direct storage for this experimentation. Next slide. Direct storage itself is not exactly straightforward. So the diagram that you see below, this is how EXR, our test EXR, had to be stored. So we had to break EXR apart into chunks, or in fact, it can be tiles. But for this test, we used a solid EXR without tiles, but we broke it down into 256 chunks. Each chunk is then fed to direct storage compression library, and what you see in purple there is what direct storage produces. So it has a header that has information about the tiles, which is what direct storage calls tiles. Each tile is 64 kilobyte in size before compression, and of course, after it's compressed, it's stored neatly in that purple little box. There is a bit of a requirement to how EXR needs to be stored for direct storage to function the way it is. Next slide, please. So this is how a typical workflow with direct storage will look like. So on CPU side, we just issue read calls, which in regards to cost is negligible. Then on GPU side, direct storage reads the data directly into GPU. It then decompresses it and provides you the structured buffer, which is what you use to decode. So decoding part is written by us, and we produce a texture out of this. The performance with the prototype went from 15 to 23 frames per second, at least 23 frames per second, which you'll see in the next slide. That is for the same 8K 16-bit RGB 192 megabytes per frame EXR. It utilizes less system memory, of course. I think direct storage still utilizes something in the background. There is less CPU work, substantially less CPU work, meaning that you can utilize it for something else. Of course, the PCIe bandwidth is reduced by 2 as well. And hard drive load is reduced by half. And of course, the disk speed is reduced by half as well. Next slide, please. So this is a snapshot before I demonstrate the videos. This is a snapshot from NVIDIA Insights. Again, you can see that the frame time in this case is 50.48 milliseconds. So going down from 75 milliseconds to 50 milliseconds. You can see that the GPU cost is spread evenly. If you look at the row actions in green, this is copying each chunk of the EXR into GPU. You can see that it does this asynchronously in the async copy engine row, which is orange row. You can see that the copy is happening, and right above it is GPU active, which is where the decompression is happening. So while the copy is happening in parallel, it also does the decompression, and GPU is utilized nicely. So as you can see, it's spread much more evenly. There is almost no CPU time in this case. And the compression ratio that we achieve with this prototype is 1 to 2. Next slide, please. So this is a sample video that I've taken. You can look at the frame rate on the left there. So average frame rate is 24 frames per second. It reaches up to 27. It's a bit varied, but it is still a substantial improvement to our 13 frames per second that I demonstrated earlier. So it's the same prototype, but instead of utilizing the conventional methods, we're using GDFlate with direct storage. Next slide, please. And this is just a summary of the benefits of this, well, what we observed by this prototype. So the file size reduced by 2, hard drive speed requirements reduced by 2, the PCIe throughput requirements reduced by almost 2 as well. The decompression is happening completely on the GPU. Almost no CPU time requires, and we do not need to juggle system memory, reducing the number of buffers that we need to be allocated and pushed through. So this is it. Any questions?
I have a question. You said Microsoft. Is there any Linux plans, or how might that be integrated with OpenEXR?
So this is one of the things that we're looking into now. We would like to utilize, instead of utilizing direct storage, we would like to try GDFlate plus GPU Direct, which is what it says up the top the slide of the slide. But in fact, it is simpler to do it through direct storage for the prototype purposes. But we are going to try NV comp library with CUDA, because CUDA utilizes GPU Direct through QFile, and GDFlate is provided through NV comp or libdeflate clone by NVIDIA. So there is a libdeflate library that NVIDIA forked.
And I think in terms of how this might impact the XR file format itself, right? The chunks that Russ was talking about, that's how the file formats sort of structured internally already. And so one of the things that I think we can investigate over the next little while is basically adding a new compression type that is guided towards this. One of the things we have to understand is whether that direct storage header is stable enough that we can basically use that reliably, that definition reliably, and then define a new compression type that we could then target. Right, and so then this would, you know, yes, you would have to have the library compiled with the right versions of the tools. The decoding, as Cary mentioned, in the EXR core library, there's a decoding pipeline that allows you to customize where the compression routine is targeted. And in fact, you can manage the memory buffers and transfers and stuff like that as well. So we think that we can sort of provide this fairly naturally, so that such that if you've got this stuff compiled appropriately, you can take advantage of this.
Mm-hmm. Yeah, if the trick with GPU Direct and GDFlate circumventing direct storage works, then and OpenEXR by itself, it won't be implementing GPU reads. We'll be utilizing the cross-platform CPU library, that the libdeflate library that allows you to read that on CPU without utilizing GPU. The users would have to implement the GPU read by themselves. So because it requires CUDA and other libraries.
One other possible place to get a little easy bit of speed back is that there is a shader after the decompression shader, which further swizzles the data and kind of unpacks it. So the decompression is just a block of data that is uncompressed after it's done. And so that could also be slightly formatted with a new compression type, so that the requirement on that is also somewhat removed, or at least reduced.
Yeah, EXR would have to be encoded to achieve the best compression ratio. So out of the box, the compression ratio is 1 to 1.6, and with a bit of a encoding and data manipulation, you can achieve 1 to 2 factor. So I skipped over it, but it's in one of the slides. But it's a lengthy explanation of how we store that stuff.
Russ, can you comment about how, because we do some of that internally in EXR already, in terms of preparing the buffer, like splitting the if it's 16-bit, right, splitting it into 2 chunks of 8 bytes each, if you will, how different was your implementation from that?
So it is very similar. One thing that we don't do that EXR already does is the predictions, or how you store the first byte of the EXR or of the chunk as is, and then everything else is a delta. So it's a delta encoding. That we don't do. We do it on the 8-byte group. So it works quite well if we take a group of bytes and then we store the first byte as an actual value, and then the rest are deltas. If we could go back a few slides, I'll let you know when. Yeah, here we go. So this shows the decoding side. So the first thing that we do, we remove the padding. Padding is essentially a header for each scan line or tile. So that's what EXR stores before each tile or scan line. Then we unpack from 32-bit. That is a limitation of GPU, because GPU data doesn't recognize structured buffers with types such as uint. It usually either packs it or pads uint8 into, or uint16 into uint32. So we unpack this into 8-byte unsigned integer. Then we convert this through magic into 16-bit integer. And then we convert the 16-bit integer to float 16, and then we swizzle. So it's as I said, it's a bit of a lengthy process. I am happy to present how we do it in one of the next presentations. So we do it in Unreal already. We just don't do the unpacking from, we do unpacking from 32-bit to 8-bit, and we skip the 2 steps in there. I hope that makes sense.
Yep. Great,
So,
thanks.
Cary, I think you had a summary slide towards the end that was just.
Any other questions about this?
No, but I think that we should also say that, look, we are going to be looking to sort of experiment with this sort of new compression type, and so the first bullet here, Cary, if you want, we would definitely encourage anybody who's interested in this to put up their hand, and we'd love to have assistance in this, right?
Yeah, just to clarify, Russ and Rod, you've written this prototype reading the EXR file format, but it's not integrated with the EXR library, right? So
No,
we're a ways away from having anything, like publicly distributable with this, right?
Yeah, that's true. And it is a very much EXR-like file, but it isn't one. That was the thing, is make it as much like an EXR so that in the event that it gets implemented for real, that it won't be a big stretch. But yeah, it was its own thing.
But obviously this would be a great thing for the community to have. So, headed in that direction is a good thing. Just to mention a few other things kind of on our wish list, new compression schemes, Z standard, some of the other, compression algorithms that are out there. We'd love to have some experiments and analysis done with that. Kind of related to that, something that we have long wanted is some kind of structured set of performance metrics. I mean, obviously performance is key for everyone in space and time, and we as the project don't have anything in the way of a set of benchmarks to gauge these things. So if anybody is keen to contribute that, we'd love to have it. Kind of related to that, example images that can be used to benchmark this this kind of stuff would be welcome. Another thing kind of on our wish list is support for BFloat 16. Just yeah. Moving down the wish list, the IMath Python bindings rely on Boost, which is kind of a pain. We would love to be free of that, and so we've thought about re-implementing the IMath Python bindings using PyBind 11. We're kind of waiting for somebody in the community to step up and actually take that on. But we'd love to collaborate. And the last is the thing we really struggle with as the maintainer community is Windows build support. Just you know, we have a little bit of it, but not as much as we'd like. So anyone that can help us out with you know, the random compile or build failures on Windows be much appreciated. And the last slide, I think, is just our contact information, the website, OpenEXR on the SWF Slack channel, or the email alias. Feel free to contact us to continue the discussion. Any other questions or topics that anybody would like to talk about?
The one slight additional note there is we didn't really say it out loud, but the compression we were talking about was lossless. And there may be other lossy compressions that could be useful for EXR in the future, but it is not where we were putting our focus.
Which is to say data lossless.
Yeah, mathematically lossless, yes.
All right, I think if there's no other questions, we could probably.
Yeah, I'll get the slides posted and mailed out this afternoon. But thanks for joining, everybody.
Thank you.
Oh, one question: will the OpenEXR Python bindings need to be a wrapper around the existing library, or as an interface, or would it be its own API? Well, to be clear, we've just had submission just a week or so ago from the existing bindings. We haven't actually looked into the implementation of them very extensively. I suspect they might need a bit of care and maintenance. Would they be a wrapper around the existing library? I believe so.
Yeah, they're a Python module, right? So it's compiled. Yeah. It's a compiled thing, right? So they may also have that same binding thing. I don't know.
Yeah.
If the question is to the design of the API, the provenance of this was that it evolved organically in the Python community as a way to load OpenEXR images and get at the data, not as a reflection of our existing API. So it doesn't have like a one-to-one correspondence to the C++ or the C APIs.
Yeah, I admit I've never actually seen the API, so I can't speak to you know, how to what it's like. So Yeah, we'll have to decide how much of that we maintain, and yeah, I think it has some similarities to the C++ API, but it's not, I don't believe it's structured in a way to be, kind of one-to-one wrapping.
Yeah, and especially because it comes from the OpenEXR 2 era, and it recently learned about OpenEXR 3, but that was an under the hood switch for them.
Yeah. Okay, well, let's call it a day then. Thanks for joining.